Welcome back. In the last outing, we had learned about the certain attributes of electric fields, and I will explain the electric fields, which is only a very useful concept. It has got no physical meaning. We'll attribute some physical meanings later on, but the electric field is defined as the force divided by the test charge in the limit that the test charge tends to 0. So what we can measure is the force acting on a charge when a charge is put at that point under consideration. Sometimes, at times, what we do is very funny, that we define electric field as force per unit charge, but the per unit charge is a very huge charge. So there is a confusion, and we should say that the force divided by a small charge q naught comma per unit charge. Okay, this comma is very important. You must bear in mind and explain that. Well, friends, I have E is equal to 1 upon 4 pi epsilon naught q upon r square in vacuum. Okay, and if I take a charge here plus q and search at a distance r as to what will be the field due to it, there is a point P. I have taken it, this is the x-axis, this is the y-axis, and this is the z-axis, which is coming out in the three-dimensional space. So naturally, as I told you, that if there is a single charge, then the lines of field will come out of it in all possible directions. Okay, normal to all these openings that we have. Okay, but I'm just taking the situation on a plane, that is, I have just taken a cut of the spherical surface which will form a circular ring over here. It's nothing, just to give you an introduction, that I have point P dash where the coordinates are 0, y and 0. Of course, this appears to be in the negative y direction. Doesn't matter, the y has a value, and that value of the y is equal to r, like the value of x over here is equal to r. Okay, so these lines are these fields that I've shown here as EP dash and EP, the 2 points. They are, in the case of plus q, they are joining the 2 points, and they are outwards away from the point under consideration where we put the charge. Well, if this were a negative charge, minus q, then the direction would be something like this, and here also the direction would be something like that. Okay. There are situations, if we look at the electric fields that we have, or for that matter any field line, set of lines, then I've just shown here that if this is the situation, then the lines of field are converging as we go away from left to right. Okay, they are converging. What it means? It means that the strength of the electric fields is smaller here and goes on increasing. Okay, because they are coming closer to each other. The closer the lines are to each other, the larger the amount of field. This is only a qualitative discussion. Similarly, in the case of lines of field, this set of lines of field, which is diverging when we go from right to left. Okay, here again, the strength of lines of field is more over here and less over here. But here in the last set of lines, I have shown them to be parallel, which means that their strength, electric field anywhere is the same. Okay, so parallel lines And the other word that need to be added to this set of parallel lines is equidistant. Okay. Now we are taking an example. This example appears in scores and scores of textbooks and books of the coaching centers, etc. Just taking this as an example, and I read it for you. And E plus, what is that? That is a proton. That is a proton. I'm not going to write here, you have to write it here. E plus falls through a distance d. This is the distance d. E plus is falling through from the positive polarity to negative polarity. I have shown a set of 3 lines which shows that the electric field is uniform, okay, to the extremes of this structure. I'll tell you what it is. Then what we do is we reverse the direction, and the electric field which was going like this is now going like this. The direction shows. I have not written E etc. over there. It's for you to see that in this kind of a structure that I have shown, where there are 2 parallel plates, okay, plate and plate, parallel plates. In the normal situation for parallel plates, these plates are maybe metallic, okay, any metal, and then I have made the situation such that this is the charge over here is minus q in this case, so the charge that is distributed over this plate is plus q. So overall, this whole ensemble, the total charge on the ensemble is equal to 0. And similarly here, it is plus q and minus q. This is called a parallel plate capacitor, or plane parallel capacitor also sometimes. Well, in most of the books, they show that this is connected to the outside world, this is also connected to the outside world with the help of a conductor. Okay, this connection is there, this is conductor, which these are also conductors. Likewise, I have the conductor here and the conductor here. Okay, and normally what the books do is that they will put these charges which I have shown as a set of positive charges and equal number of negative charges on this. They show it on this side, on the upper and the lower sides. No, no sir. The charges exist inside only. The outside of the capacitor, I am telling you in advance to you, is never charged positive or negative. Okay, the charge on the outside of the capacitor, if the plate is like this, the upper plate is like this, then the charges exist over here. This is charged less. There is no charge on the outside. Okay. So this is the schematic diagram for what we are desired to do. This is separation D, and I have taken also here the separation D, where we are going to make a free fall under gravity. Okay, so it is 3 parts. Part 1 is that the proton falls. Part 2 is that the electron falls under the influence of 2 electric fields which are equal in magnitude. Okay, and they are separated by the same distance. And the third is they want to contrast you the situation with that of free fall of the proton and free fall of the electron under gravity. I'm just going to help you. I'm going to help you only. I'm not going to solve these things. That's why I've not taken the charge of the electron as minus 1.6 into 10 to the power of minus 19 coulombs, and that on the proton plus 1.6 into 10 to the power minus 19 coulombs, I know that in a matter of days you will remember these charges in proton and neutron. 1.6 into 10 to the power minus 19 coulombs. One is proton is plus, electron is minus. There's no problem. So now let us see, by definition of the electric field, okay, I can obtain this equation as F is equal to the charge Q into E. And therefore in this case I have taken small e as the charge, so F is equal to, I am just taking the magnitudes and not bothered about the plus or minus, etc., etc. What is this, what is that? Okay, like a student who has been just introduced to the thing. So magnitude wise the force is equal to E into E. Okay, by the definition of E, by the definition of the electric field. Okay, in terms of the force, and the force by Newton's second law is defined as the mass into the acceleration. So I can write ma is equal to E, no problem. So A will become equal to E upon m. Okay, it's very simple. Now let's go to this far. We have dealt with the dynamics part or kinematics part, okay, of the problem. Now we go and say salam to the kinematics part. What happens? Because the magnitude of the electric field is the same, the charge is the same, the mass is the same, therefore the acceleration during this motion will be the same. During this motion the acceleration is the same, and when there is nothing, then also the acceleration is the same. That's the small g, which is gravitational field in this case, or acceleration due to gravity. So when I say salam to the and tell kinematics that I have a situation where there is constant acceleration, and I have initial velocity u and a time of flight or time associated with the fall or journey or whatever is t, and I have a distance d which I have to cover, then they will say, well, you go for the second equation, s is equal to ut plus half at square, which is also written as x minus x naught is equal to u naught t plus half at square. Okay, it doesn't matter. So we have the formula, the beauty of kinematics for constant acceleration, that s is equal to ut plus half at square, and we do take that u is equal to 0, that my electron or the proton, they start with a 0 velocity. Okay, u is equal to 0 and s is equal to d. So I will write from here d is equal to half ad square and a is equal to e upon m. So I get this formula, and therefore I can write the value of t. T square is equal to 2md upon ee. So t becomes equal to 2md upon ee, where e is the charge on that. Okay. Now I can compare. You can take the value of the mass of the electron, mass of the proton, and put it here at the top plate, and switch the charges off. What will happen? Because of their mass, because of the acceleration due to gravity present, the constant acceleration, they will start falling, gaining in their speed. Okay. And with a similar thing, I can get it, because s is equal to ut plus half at square, so s becomes equal to 0 plus half gt square, okay, which I am writing over here. You can calculate the value of t in a similar manner and then make comparisons on your own, and you will find very, very interesting things. Well, I have a formula here. I told you some time back that physics starts when the formula has been derived. And here, look here. The 2 is the same, D is the same, E is the same, capital E is the same. What is not the same in the case of electron and protons? The mass. So the mass of the proton is 1870 times the mass of the electron. You have to search that. I'm not going to tell you right here and there and waste your time on that. Okay? So you have to search and learn and do it. You have a book and you can scribble on that. So you are the king. I told you, you are the king of Tartary. You are the male king or female king of Tartary. Okay. I will not call a female a queen. No. You are not a queen of Tartary, you are a king of Tartary. So you can do anything you like. And then you compare these things, and what is the end result when you compare these things? When you scribble out, when you finish up with that, you are happy, you are glad, you enjoy, you know that you are a somebody, and you are a somebody, yes. So I take another example, okay, and explain out the things in the office. So this is another example, a favorite example with teachers, where charges plus q and minus q are placed. I'm writing held at two vertices of an equilateral triangle as shown. Okay. The diagram is not up to the mark. Okay. Calculate the electric field at the point A, at the point B, and at the point C. The point A is in between these two charges, plus q and minus q. This is, these sides are L, L and L, so this is L by 2, this is L by 2, and this one is also L by 2. Okay. So I have shown the electric field due to the positive charge in this direction is like this, and due to the negative charge also it is in the same direction. So the resultant field will be twice this value. Let's take the point B. The point B is close to the positive charge, and therefore the electric field contribution due to it will be much more as compared to what it is, because it is far off 3 times at the distance from minus q. Therefore this will be small and this will be large, and the resultant will be away towards this positive charge. Okay. If we were taking this point B on this side, then we will have it is still coming like that. Okay, the same direction of the net, but this is like this. Okay. At the point C, due to plus q, the field will be away, which I have shown as EC plus, and field due to the minus q will be in this direction. Both must be equal in magnitude. Okay. And then because this angle is 60, 60, 60, this angle is also 60, this angle is also 60. Then if I take the resolved parts for this electric field along the x-axis, then and along the y-axis, then those parts which are along the y-axis will cancel out each other, because their magnitude will be equal to something into sine of that angle that it makes there. sine of 30 degrees, sine of 30 degrees, like that. Okay. And here I'm sorry, it's cos of 30 degrees, cos of 30 degrees. Okay. Or sine of 60 degrees, sine of 60 degrees, like that. So the resultant is that the two are added together and C net plus is in this direction, which is parallel to the axis of these two charges, and we can calculate like this. I carry out the calculations because each of EA plus and EA minus, that's equal to this, it will become equal to and the two are added together, so it is like this, 8 times 1 upon 4 pi epsilon naught q upon L square. Similarly for B, this point B, you can see that I have taken one part as like this, and the other part is 1 upon 3 n upon 2 whole square, which I work out and we get it like this. Okay. And similarly in this case, I take 1 upon 4 pi epsilon naught q upon L square cos of 60, which is half and half and half and half make 1, and therefore the value turns out to be like this. Okay. So with these two examples, I have set in and I have given you an idea how the things will be done. I close it here and we'll talk more about the electric field, okay, later on.